So it's up to you. You may also want to have both your blue and yellow sheet in front of you. I usually have the yellow sheet open to all of the constants, the mass of the Earth, the radius of the Earth, the radius of all the sun stuff, and I have my blue sheet open to the equations. Or like a peon, you can just flip them back and forth if you really, really have to. It works with one sheet as well. The key idea we said last day was if we are in orbit, we can immediately say gravity is what's pulling us in a circle. In fact, last day I said to you there were 4 ideas. There was orbital radius, orbital speed, orbital period, and orbital altitude. I said if I give you any one of those, you can find the other 3, because we said for altitude, if they give us the altitude, we can get the orbital radius. It's just add the radius of the planet, the Earth, or whatever body that you're orbiting. You can memorize or write down these various equations. I would encourage you just to do the derivations. So we got all the way up to and including example 6. I think with you folks, we watched the gravity visualize the stretchy sheet of Lycra as an illustration of gravity. We did watch the astronaut playing baseball, and I think I showed you the Chris Hadfield video as well. So example 6, a satellite has an orbital altitude of 1.2 times 10 to the 6th meters above the Earth. A says, what's its orbital radius? Isn't it 1.2 times 10 to the 6 meters? No, that, Ethan, is how far it is above the Earth. If we were to draw a little picture, if that's the Earth, they've given us that distance, the altitude. We would like this distance, the radius. How can I figure out the radius if I know the altitude? Yeah. So our orb is going to be 1.2 times 10 to the 6th plus our Earth, which is 6.38 times 10 to the 6th, I think. I think I can do this in my head because they're both 10 to the 6s. It's really going to be 6.38 plus 1.2. Is it 7.58 times 10 to the 6th if you use your calculator or do it in your head? That's its distance from the center of the planet. So if they give me the altitude, I have to use it to figure out my orbital radius. But after that, everything else is good. We're good to go. James, what's B want me to find? Did you say orbit? Gravity is what's pulling me in a circle. We're going to be using Newton's universal law of gravitation. So it's going to become big G, big M, little m over r squared equals, and then, James, I think to myself, MAC, but which version of AC am I going to use? How do I know? Because they asked for or mentioned the speed. Did they need to tell me the mass of the satellite? It's a good thing, because they didn't. Does an R cancel here? Yeah. In this one, an R cancels. In the other version, an R does not. But in this one, an R cancels. And in fact, I can get rid of the squared by square rooting. I get orbital speed is equal to the square root of, what's big G? More specific as a number exactly?
6.67.
I'm just going to write big G. But I'll type 6.67 times 10 to the negative 11. Mass of the Earth? All over. I'm going to write 7.56 times 10 to the 6th, but if you're lucky, you've got that sitting on your answer button, and you can just use your answer button. I know orbital speeds are in the thousands. I know that if I'm orbiting right by the Earth, I think we calculated that last day with the football. I think it was something like 7,900. So this will be a little less than that, because the further away you go, the slower you need to be traveling to orbit. So you're going to get something in the thousands, and it's going to be less than 7,900. That's about as much as I can give you for accuracy. And again, I would strongly encourage all of you to practice typing these, because every year there's some kid who gets all the wrong answers with all the right writing. And I just, oh, you didn't bother practicing. James, what'd you get?
7,256.
So 7260, if I go to 3 sig figs, is that right? 7260? No? Yes? Let's see. No? I need nods. No nod? Okay. Oh, I got one nod. Evan, is that what you got?
I got 7,250.
Did you use your answer button? Is it 725? What's after the 5? Is it? You said 7256?
Yeah, 7256.
Is it 7256 or 7254?
I got
7254?
7254.
7254? And times 10 to the what? Oh, just no. Sorry, just in thousands.
Yeah.
I'm double check. Maybe you made a digit typo.
It should be.
Oh, I know what it is. You're using your G button on your calculator, aren't you? Okay, you're using your G button on your. Oh, yeah.
It should be 7.58, not 7.
Oh, I can't write. Read. 7.58, like that.
Yeah.
Thank you. That's what happens when I do math in my head. So you were correct with my bad numbers. 7,000. What is it, Evan? 1,250 meters per second. Okay. Assuming you don't make any silly mistakes like copying stuff down wrong, like I just did. C. C. Ethan, what does C want me to find? Did you say orbit? Gravity. Now, by the way, just because it says orbit doesn't mean you have to write gravity is what's pulling me in a circle, but you certainly can every time. Gravity is what's pulling me in a circle. I'm going to get big G, big N, little m over r squared equals little m. Ooh, Ethan, what am I going to write now for the acceleration? Yeah. R over t squared. Does little m cancel again? Really, by the way, what we're actually saying is the accelerations are going to match each other up there. We're accelerating in a circle because we're in free fall acceleration. This right here is what we called little g. I mean, technically we're saying this. Little g equals AC. Right? What are we trying to find? A common sloppy mistake that I see, kids forget that this t is on the bottom. And so they just go, I'll divide by 4 pi squared r. And then they square root. What they've really just found is the reciprocal of the period. So if you're ever solving for the period and you get an answer way smaller than 1 second, you probably have made that sloppy mistake. Double check, because the periods are typically going to be in the thousands of seconds. So where is the t right now? On the, yeah. I'm going to multiply it to the top. That's going to give me a t squared. There's a 4 pi squared on the other side. Is an r going to cancel here? I'm going to get an r cubed. And I think big G, big M, and then I'll square root that. Okay, next common sloppy mistake. Someone did this earlier this morning. They wrote the cubed. They thought the cubed. Their thumb, without even thinking about it, hit the squared as they were typing, because it's such a habit, because that's been the exponent we've used the most. So when they gave us the answer, I did some quick thinking. I said, I'll bet you hit a squared instead of a cube. What? How did you figure that out? It's a common mistake. Let's plug in our numbers. But I'm going to abbreviate a little bit. At least I'm going to abbreviate the G. 4 pi squared 7.58 times 10 to the 6th. Was that right, Mr. Dewick? Finally. Don't forget the cubed. All over big G 5.98 times 10 to the 24th. I know the International Space Station orbits every 96 minutes, which is roughly every 100 minutes, which means it's about 6,000 seconds. You're going to get somewhere in the 4,000, 5,000, 6,000, 7,000 second range. Excuse me. Ethan, what'd you get? Okay. Plugging away? Okay. Thumbs up. What'd you get? I waited for you to give you the glory. And the Oscar goes, oh, they're not here. Never mind. Let's give it to somebody else. Tom, what you got? 6,570 if I go to 3 sig figs. And that's seconds. Do me a favor, divide that by 60. Yeah, it's about right. I just know a standard orbit is around 100 minutes, give or take. There's as you go further out, yes, it gets longer, but that's just nerd trivia. You don't need to memorize that, but I always like to know my ballpark figure seems right. So I think we've done in that lesson one of every possibility. I gave you a speed, find radius. I gave you a radius, find a speed. I gave you a period, find a... If I give you any one, you can find the other three. What's your homework? Number 1 is good. Number 2 is good. Mr. Dewick, you want me to find the speed at which Mercury orbits the sun? Yeah. You didn't give me the mass of Mercury. No, I did not. You didn't give me the mass of the sun on your sheet. And I did give you the orbital radius. By the way, I may have mentioned this last class, but one of the really neat things about this equation right here is the big M does not cancel. And so this is how, with the 1700, 1800 technology, they were able to figure out the mass of Saturn or of Jupiter. You would observe one of their moons and you could calculate by telescope observations their radius and measure their period, and then you would get the big M by itself and you had the mass of the planet. And we still use that technique for nearby stars. If they have any planets around them, we can use that to get a pretty good accuracy, a pretty good measurement of what the mass of the star must be, for what it's worth. So, number 2, I think I said. 3 is good. We're above the moon. Please notice I gave you the radius in kilometers. You'll have to make that meters, or I think it's on your formula sheet, as a matter of fact. 4 is good. 5 is good. 6 is good. 7 is kind of cool. 7, we're talking about geosynchronous orbit. A geosynchronous orbit is when a satellite appears to stay above the same place on the Earth at all times. So the Earth is spinning, but the satellite stays above the same location. What must the period of that satellite be exactly in hours? 24. Could you please convert that to seconds? On your calculator, could you go 24 times 60 times 60? Nine is good. Skip 8. 10 is good. 10 is challenging. Your hint is, I've told you the gravitational field strength. You can figure out how far you are from the center of the planet based on that. Not 9.8, but you can figure out what R is, and then you can figure out the speed. Skip 11. 12 is good. 13 is good. 14 is good. 15 is good. I've just thrown a whole bunch of work at you. We're going to start the next lesson. I'm going to get partway through it because I want to see if I can't give you lots of time on Wednesday I want to finish off the lesson, give you lots of time on Wednesday, and that way you can go into your 5-day weekend with minimal amount of homework, okay? So normally I'd say, here's some time to work on this, but I want to start the next lesson. We're going to start the next lesson. Cosmic potential energy, or orbital potential energy. But since we're not always going to be in orbit, I'll just call it cosmic potential energy, the potential energy equation for the universe. First of all, why can't we just use mgh in outer space? Little g is changing. Yeah. Yeah. Who's in calculus here? Raise your hand. Calculus students, I'm going to give you a calculus explanation, but then I have to give the non-calculus peons a good explanation as well. So I'll be giving 2 explanations today. The calculus one is much more elegant because it comes out in 2 lines. So if we can't use mgh, what can we do? First of all, recall the area under a force versus distance graph. So put a little f and a little d. Draw kind of a line going up at a slant. But this time what I'd like you to do, draw a line down, put a lowercase a there, draw another dotted line, it should be dotted lines, dotted line down, doesn't matter really, but put a little b there. And then you can completely color it in, or just kind of do that like I just did. What is the area under a force versus distance graph telling us as a physics idea? Well, it's area. I gave you 2 tricks. One for slopes. I said to interpret slopes, since it's rise, over, run, just divide the units or the variables. But I said for area, what mathematical operation appears in every area equation anywhere? Think about every area equation you've ever learned, and you're saying in that equation a certain mathematical operation. Yeah, so multiply force times distance. What is force times distance? What? Say it again. What? Right from your formula sheet. But now I'm going to be fussier. Actually, you can put the word work in the blank here, but I'm going to be even fussier. The area is the work required to move an object from A to B. That area is the work that was required to move this mystery object from location A, whatever it is, to location B. We're going to apply this same strategy to a graph of not just force times distance, but gravitational force times radius out from the center of the planet versus radius out from the center of the planet. So it's going to look like this. Put an FG on your y-axis. Put an R for radius or separation distance on the x-axis. What is Newton's universal equation for gravity? Fg equals big G. Keep going. Anybody? Big M over. Here's what I really want you to notice. This graph depends on 1 over r squared. Yes, big G, big M, but there's the r squared's on the bottom. And that's your x variable in this graph. In pre-calculus, I think you folks have done transformations. You did slides, expansions, and compressions, and you did the reciprocal graph, the reciprocal transformation. Thomas looked a little pained there. Thomas, all I want you to realize is this is going to be the reciprocal of a parabola. It's an x squared graph. No, it's a 1 over x squared graph. What does that look like? Kind of as a shape like that. It's that curve. My steepness might not quite be accurate, but I haven't put any numbers on there, so who are you to judge? It could be. We're going to redraw this graph. So FG, R, and kind of put this shape in there. But once again, we're going to add a location there and the location there. I'll call this location A. I'll call this location B. Again, some dotted lines. Again, color, 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 color. Or you can just draw it like that. Now, this is still work. But what does the area represent here? The area is the work required to lift an object from, and then pause after the word from. Instead of A and B, which are okay, underneath the letter A, how about put our Earth? And underneath the letter B, how about put our orb? So this would be a graph. If I knew how to find this area, the area would tell me the work required to lift an object from the surface of the Earth to some preferred orbital radius. Now, this isn't enough to put it in orbit. This would just get it to the right height. It's still going to come crashing down. You're then going to need to fire your rockets and give it kinetic energy to keep it in orbit, because you got to give it that V orb, the square root of big G big M over R. The problem here is this. What the heck is the equation for the area of a curvy wedge like that? Calculus students, the final 25% of the course, probably you'll start it around beginning of May, is finding areas underneath curves. But I'm going to spoil the punchline right now. It's the antiderivative. You've all learned how to take derivatives, okay? Reverse the procedure, and that's the area. So, instead of subtracting one from the exponent, I'll add one to the exponent. Instead of multiplying the number to the front, I guess I'll divide the number on the... That's for the simple power law. You reverse the power law. But this is called integration. Integrals give you areas. Derivatives gives you slopes. Integrals give you areas. Non-calculus students, we got a problem because you don't know calculus. So I'm going to do some hand waving here. This is going to give us the right answer, but it's technically bad math. I'm going to say this. Since work equals force times distance, I'm going to go work equals big G, big M, little m over R squared times R. That is a force times a distance. Which force? Gravitational force. Which distance? Distance from the center of the planet. Oh, one of the R's cancels. This is the equation for cosmic potential energy. Can you all write PE and then equals, leave a space, big G, big M, little m over R. But where I said leave a space, stick a negative. The negative does not pop out of this derivation here, but it is negative. Why negative? Who are my calculus students? Because the derivative of this is force. If you take the derivative with respect to R, well, this would be an R to the negative 1. You would move the exponent to the front, which would give you a negative. Times that negative that I have there gives me a positive force, and then you would subtract 1 from the exponent, making it R to the negative 2. It would end up down, and you would end up with big G, big M, little m over R squared. Okay. Non-calculus students, that was gibberish that I just said to you, but calculus students, take the derivative of this, you have to get force. So if I don't put the negative in there, I get negative force, which is not what I want. We had to define zero energy, zero potential energy somewhere. And we decided, Kiefer, that zero potential energy means you're not going to fall if we let you go. Look up. Did it fall? It has potential energy. What if I went further from the Earth with this? Would it still fall? Yeah, gravity would be weaker up there, but it would start to fall. And in fact, it would accelerate because the closer it got to the Earth, the stronger gravity would get. It would have potential energy. Where would it not fall? Out at infinity. So far away from the Earth that the gravitational field is zero. So we talk about relative to zero at infinity. And what we mean is because we could have let, I guess, the surface of the Earth be zero potential energy, but that's very egocentric. We want to go cosmic. Let's let zero potential energy be where there's no gravity. And where is there no gravity? At the very edge of the universe, all the way out at infinity. So here's my little planet analog, or my asteroid or satellite right here. Look up. Let's pretend it's out at infinity, and once again, Kiefer is the sun. If I let it go, will it fall now? No, because no gravity is reaching it whatsoever. Okay? Now, for me to get this out to infinity, I would have needed to start near Kiefer and pull it, because it wants to fall to the sun, and pull it, and pull it. I would have had to exert a force over a distance. I would have had to do work. But I ended up at zero potential energy. I had less potential energy here, more potential energy, because I'm going higher, but here I end up at zero. What type of numbers can you start out less than and end up at zero? How can you possibly start out somewhere, add energy, and end up with zero? Well, you better be starting with negative. So we're going to define the area near a planet as having negative potential energy. And what we're saying is, because you have so much negative potential energy, you're going to have to add a whole bunch of energy, do a whole bunch of work to get it out to infinity, to zero. That's why there's a negative. Regardless, on your formula sheet, if you look for this equation, there's a negative. I think you'll also notice it's the last equation of this unit, I think. Is it not? So why negative? Out at infinity, at the edge of the universe, an object would have zero potential energy, since it's not being affected by any gravitational field at all. It can't fall anywhere. If our height is less than infinity, we have less potential energy. What numbers are less than zero? And so we use the phrase relative to zero at infinity. In fact, often in the notes or in the questions, you'll see me abbreviate it as RTZAI. That's my cue. You better use the cosmic potential energy here, please. But honestly, if you're leaving the planet, use the cosmic potential energy equation. Negative big G, big M, little m over R. Example 1. Example 1, write small. I've learned the hard way I didn't leave enough room to easily show work. I like example 1. I like example 1. Example 1 is a nice question. A mass is released from a height of 6,300 kilometers above the Earth. First of all, am I going to do physics with kilometers? Could you please multiply that by 1,000? What do you get? 6.3 times 10 to the what? 6 or 7? 6? Meters. How fast will it be going when it hits the ground? Caleb, what's this question asking me to find? Speed. It says ignore air resistance. Key question. Are we in a stable orbit? First of all, do you see the word orbit anywhere in this question? Okay. Secondly, if we are in a stable orbit, are we going to come crashing into the planet? No. Are we crashing into the planet? Are we crashing into the planet? So are we in a stable orbit? No. So can I say gravity is what's pulling me in a circle? No. Okay. What's it want me to find? Caleb? Ignore air resistance. Is there a change in speed? Is there a change in height? Is there a yucky curvy graph? You know how I'm going to solve this? Yeah, cosmic conservation of energy. And unfortunately, this is going to be a lot of writing and a lot of typing, and that's the universe we have. Suck it up. So I'm going to start out same old by going KE initial plus PE initial equals KE final plus PE final. Normally here I would say, are any of these zero? But I'm going to pause for a second. First, we're going to substitute in all of our equations because this is pretty complicated. So I'm going to write this as a half mv initial squared plus mg. Oh, no, I can't go mgh. Are we cosmic here, Caleb? Plus negative big G, big M, little m over R initial equals a half m v final squared. I love digital ink. Plus negative big G, big M, little m over R final. Are any of those zero? Let's look at the kinetics first. Is my speed ever zero? I think released implies dropped. Oh! Ha! I noticed something else too. Do you see it? Before that. Before that. Yes? An object's mass will not affect how fast it hits the ground. It'll affect how much damage it does when it impacts. Yes, thank you very much. And so we will later on look at questions involving work and damage, and M won't cancel there. But in terms of just how fast it hits, little m cancels, especially if we're ignoring air resistance. What are we trying to find? Which is that right there. This is where my love for rewriting equations ends. I'm not going to get the v by itself for a while. I am going to get this over to this side. So I'm going to make a little note here. I'm going to plus this to that side, and I'm going to rewrite this. I'm going to get negative big G, big M over R initial, stayed where it was. But then there's going to be a plus big G, big M over R final. That equals VF squared over 2, or a half VF squared, or 0.5 VF squared. James, however the heck you want to write it, I don't care. I am now going to choose to crunch this as a number, then I'll times by 2 square root. I'm not going to try and get the v by itself yet. Why not? Patience. Draw a little arrow like that. We have negative. What's big G? Put your calculator down, James. And I'm dead serious. Nobody pick up your calculators yet. Put it down. No touch. Big G, I'm just going to put big G, 6.67 times 10 to the 11. Mass of the Earth, James? All over. R initial, it seems to me R initial is the radius of the Earth plus 6. I don't know why I put an 8 up there. I wrote the radius of the Earth up there, didn't I? It's just 6.3 times 10 to the 6. That's a habit. I think our initial radius is the radius of the Earth plus the altitude, which is R Earth plus 6.3 times 10 to the 8th. No calculators yet. James, you agree with me there? Sixth. Why do I put an 8? Because I can't read my own writing. Thank you. Sixth. You okay with that so far? Then what am I going to write? A plus sign. Then what? Did I already write big G? And I'm doing this on purpose, both to be lazy, but to actually show you what I'm doing on my calculator. Don't write it yet, James. Instead, I'm going to put a ditto mark, a quotation mark, times. Then what am I going to write? Same thing? Ditto mark. In other words, I'm going to say, I've noticed the top doesn't change in both of these fractions. And it does not. All over. What's my final radius, not 0? Radius of the Earth. And that's one, people are, isn't final potential energy 0? No. Where is potential energy 0? Out at infinity, which we're not at. So I'm going to go R, Earth, that equals V final squared over 2. Now you're going to pick up your calculator and you're going to go step by step with me, please. This is what I've tried a bunch of different variations. James, this is what I've found is least typing for maximum organization and most important, fewest stupid mistakes and typos. Ready? Type in negative 6.67 times 10 to the negative 11. Negative G. Already made a typo. And go times 5.98 scientific notation button 24 divided by bracket 6.38 scientific notation button 6 plus 6.3 scientific notation button 6, close off the bottom, and don't type anything more, just the first term. And you should get negative 3145630.9.15. If you didn't, now is a chance to kind of get my attention. Is that right? I'm going to write that down. Negative 3145630.9.15, and then I'll put a plus sign. This is actually why I went on the big rant last year about getting a good calculator, because if you have a good calculator, and I hope by now all of you do, you should be able to just backspace or left arrow or up arrow, and you should be able to go to this same expression, delete the negative, and delete the 6, and that should be the second fraction. So what I'm advising Abby is type in the first expression very, very, very carefully, making sure you make no mistakes, and then you can edit and get the second expression without having to retype it and introduce the possibility of mistakes. I get 6251818.182. 6251818.182. That equals VF squared over 2. You okay with that, Francesca? This is what we're going to do for the cosmic potential energy equation, because we're going to notice almost always you have the same thing on top in both fractions. Use ditto marks, use backspace, just change what you need to. Carry it to about 5 or 6 or more sig figs so that you know you're going to be bang okay. I need to add these two numbers together. Well, that's pretty easy. It's going to be negative 314,563,09.15 plus, haha, answer button. And I get 31061872.67. I get VF squared over 2 equals 31061873.1. 1872.67. Caleb, you get the finish. How would I get the V by itself? times 2, then square root answer button. I get 7,880 meters per second. Which is pretty fast. It'll do damage. Okay. What were we being asked to find in that question? How much what? Or speed. What are we being asked to find in example 2? How much what? Work, you say. Here we're going to use the work-energy theorem. The notion that work is the change in potential plus the change in kinetic. However, because it's important, I don't want Annika to miss it, we're going to pause here. You have the remainder of class to work on the orbit homework that I gave you.